Hello everyone, welcome to the lecture 48 in the course Diffusion and Solids. Last two videos of this week we talked about the intermetallics and also the nanocrystalline material. Today a brief video is dedicated to diffusion in another exciting class of material which is known as a quasicrystalline materials. I don't know if you have already heard about these material, what is quasicrystalline, because we talk about crystalline or amorphous. What is the quasicrystalline material? So we will talk briefly about quasicrystals and some features of diffusion mechanisms in them. So quasicrystal, in this case the atomic positions are ordered, but with 5, 8, 10 or 12-fold rotational symmetry, which so to say violate the canonical rules of the classical crystallography. When classical crystallography people talked about the principles, certain symmetries were not allowed, and those symmetries are the ones which are exhibited by these quasicrystalline alloys. So this discovery of the first quasicrystal Al86Mn4 was announced by Shetman and in 1984. So this was the paper in which this was reported, Dan Shetman. So these are the examples of the crystalline phases. So these are icosahedron phases. This is how a dodecagon looks like. You can see a pentagonal symmetry. Also, there are also decagonal quasicrystals. So these are the various examples of the quasicrystalline phases and the structures in which they crystallize. So in the quasicrystals, the transport measurements have revealed usually high electric resistivities in aluminum-based alloys. Mechanical properties conducted show brittleness and hardness at low temperatures, but very high ductility at high temperatures. These quasicrystalline structures are complex because there is no periodicity, and these are mostly ternary, quaternary or multi-component alloys. So quasicrystals have the rotational order and sharp diffraction peaks. So remember, they are not amorphous. They have a structure. They show the diffraction peaks, sharp diffraction peaks, but they do not exhibit a translational symmetry. So this is again a decagonal structure which is based on the Penrose tiling. Now I said that quasicrystalline structures are not a periodic structure. So what people try to still mathematically understand, and they exhibit what is known as quasi-periodicity. So first of all, let me show you this example. These are the SAD patterns of a C14 structure in the 100 zone axis. Okay, these are the standard structures. So you will see here these are sharp periodic spots, regular spacing between two spots. So between two spots you will see a similar spacing. The spots which corresponds to one plane, they are equi-spaced. Whereas if you come to a SAD pattern of the quasicrystalline phase displaying 10-fold symmetry, so you can see already this is 10-fold symmetry. There are sharp spots, but they lack periodicity. So these show long-range ordering, but no translational symmetry. So they have a rotational symmetry, they have a 10-fold axis, but they don't have they don't show what is the classical translational symmetry. Instead, what they show is what is known as a quasi-periodicity. What it means is that periodicity, when we talk about, typically we talk about in terms of in a particular direction, you will see the atoms are equally spaced. However, in the quasi-periodicity, they do have you can say a periodicity, but these atoms are not equally spaced. These follow a certain order, but these are not equal, or these are not periodic in the classical terms. What we mean by quasi-periodicity, I will just try to elaborate a little bit more in the next slide. So it refers to a unique atomic arrangement where patterns repeat with a specific mathematical relationship, but not periodically like in normal crystals. That means if there are 4 spots in a quasicrystals or 4 lattice points, so to say, in a quasicrystal, there will be a certain relation between them. but it may not be the case that it is not the case that these 4 spots are equally spaced, which is what you generally find in the normal crystalline materials. So, that is what is referred to as quasi-periodicity. So, this is the arrangement where the patterns repeat, but with a specific mathematical relationship, not like the normal crystals. So, mathematical analysis reveal that these periodicity is related to the Fibonacci sequence and the golden mean. What is the Fibonacci sequence? It is, you can see here 1, 1, 2, 3, 5, 8. So, each term is the summation of the previous 2 terms. For example, if you see 2, it is 1 plus 1, 3, it is 2 plus 1, 5, 2 plus 3, 8, 3 plus 5, and so on. This is known as a Fibonacci sequence, which is a sequence in which element is generated by adding the 2 preceding elements. In other words, xn can be written as xn minus 1 plus xn minus 2 for every n greater than 1. So, now if you calculate the ratio of these successive terms, this is first 2 terms, the ratio is 1, then the third 2 is 2 by 1, 3 by 2, 5 by 3, 8 by 5, and so on. Now, what people try to do, they try to plot this ratio as the number of terms in the Fibonacci sequence increase. So, if you try to plot this ratio of this ratio as a function of n, you will see that the n reaches a mean value which is close to 1, which is as 1.618. Okay. So, if for the large number of values of n, this reaches the ratio reaches a mean which is equal to 1.618. This is known as a golden mean. So, this constant is the golden mean, and this is used to define the periodicity or the quasi-periodicity in the quasicrystals. So, how the golden mean defines the periodicity? For example, if you see the distance between transmitted spot and first spot is d1, then the distance between transmitted spot and the second spot is d1 into tau. So, this is how the golden mean, and then you can have 2 taus and so on. So, this is how the quasi-periodicity is defined. The spots are related by a certain golden mean, but they are not equally spaced, so to say. Now, let us move ahead and talk a little bit about the diffusion in this quasicrystalline phases. So, extensive diffusion studies on single quasicrystals have been performed on the icosahedral phases, aluminum, palladium, manganese, and zinc, manganese, rare earth, and on the decagonal phases Al, Ni, Cu. Now, since the natural aluminum is monoisotopic, the self-diffusion studies through radio tracer technique and SIMS have been absent in the Al dominated alloys such as icosahedral Al, PD, Mn, and decagonal Al, Ni, Cu. So, you have seen from the table previously that many of the alloys are rich in aluminum, especially the icosahedral, some of the icosahedral alloys. But unfortunately, aluminum isotope is not available. It is the natural aluminum is monoisotopic. So, therefore, you cannot use radio tracer and the SIMS to understand the self diffusion. In fact, people have tried, for example, zinc to mimic the aluminum diffusion or self diffusion, or gallium to mimic aluminum self diffusion, and reasonable agreement has been found out. So, in the quasicrystalline alloys, therefore, the solid diffusion studies in such alloys are more prevalent. The icosahedral quasicrystals, these are highly symmetric quasicrystals. The diffusion is isotropic, and the diffusion coefficient therefore is a scalar quantity. Decagonal quasicrystals are uniaxial, and diffusion coefficient therefore has 2 principal components. One corresponds to diffusion parallel to the decagonal axis, and another one diffusion perpendicular to the axis. Now, let me list a few features of diffusion in icosahedral aluminum, palladium, manganese. This contains about 70% aluminum, 20%, 21% palladium, and 9 atomic percent manganese. This is not a stoichiometric compound, but has a very narrow phase field which widens with increasing temperature. So, in this particular alloy, self-diffusion of manganese and palladium has been studied, as well as the solute diffusion of transition elements, cobalt, chromium, iron, nickel, gold, and non-transition elements like zinc, gallium, indium and germanium has also been investigated. So, the non-transition elements are relatively fast diffuser. The diffusivities are comparable within one order of magnitude to the self-diffusivity of metallic aluminum. These gallium and zinc, as I said, were used to mimic self-diffusion of aluminum in the quasi-crystal. The diffusion of transition elements is relatively slower, sometimes extremely sluggish. For example, diffusion of iron at 700 Kelvin is about 7 orders of magnitude slower than gallium and zinc diffusion. This is a huge reduction. So, the transition elements diffuse very slowly in this icosahedral aluminum palladium manganese alloy. Therefore, the corresponding result is also reflected in the activation enthalpy. The activation enthalpy for or energy for Fe, cobalt, chromium is almost double that of gallium and zinc, although their denotes are quite similar. Now, the pressure dependence of manganese and zinc has also been studied in this icosahedral aluminum palladium manganese alloy, and what people see is that activation volume of zinc is close to 0.74 omega. Omega is the atomic volume at 776 Kelvin, whereas for the manganese it is about 0.67 omega at 1023 Kelvin. So, the activation volumes interestingly for the transition and non-transition elements are nearly same, indicating that the diffusion mechanisms are similar. Whereas you saw the when it comes to as such the diffusivities, we saw that the transition elements diffuse much slower. So, the signs of these activation volumes as indicated here also these are positive, and these are attributed to the vacancy mediated diffusion. So, in addition to vacancies, there are certain additional point defects known as phasons for the quasicrystalline materials, and the flip of these phasons, we are not going into that mechanisms. Just to make you aware, I put this point that there are certain additional point defects which come in the quasicrystalline materials, which are phasons, and their flip in some cases can contribute to self and the solute diffusion. So, diffusion of zinc and gallium in icosahedral Al palladium Mn and diffusion of zinc and gallium in aluminum, they obey very similar Arrhenius laws, which suggests that zinc and gallium diffusion in this alloy is also vacancy mediated and restricted to the Al subnetwork of the quasicrystalline structure. So, this is important how the people who study diffusion tend to draw the inferences. You see that zinc and gallium in the icosahedral AlPd manganese show similar activation parameters than as for diffusion of zinc and gallium in pure aluminum. So, what it suggests is that in the quasicrystalline alloy aluminum palladium manganese, the zinc and gallium diffuse primarily through the Al subnetwork. Then some points about the diffusion in icosahedral zinc, manganese and rare earth alloy. So, in this category of alloys, the prototype these are the prototype of non-aluminum based quasicrystalline alloys with zinc content of about 60 atomic percent. These quasicrystals are considered to belong to the Frank-Caspar type phases, for which the electron to atom ratio is generally about 2.1. There are three major quasicrystalline phases that have been found in this category of alloys: a face-centered icosahedral phase, a simple cubic icosahedral phase, and a phase with a decagonal structure. So, in this Zn diffusion is closely related to ZnMgHO and ZnMgY quasicrystals and proceeds at almost identical rates. Zn diffusion in these quasicrystals is slower than self diffusion in metallic zinc, which can be attributed partly to the different melting points of zinc and these alloys. So, in this Zn diffusion in icosahedral AlPdMn proceeds about 1 order of magnitude faster than zinc diffusion in the Zn based quasicrystals. And here also the vacancy mechanism is seen to be playing a major role. Diffusion in decagonal quasicrystals. So, these decagonal phases are the two-dimensional quasicrystals and exhibit quasi-periodic order in layers perpendicular to the decagonal axis and periodicity parallel to decagonal axis. So, you have quasi-periodicity when you talk about perpendicular to decagonal axis, but periodicity when parallel to the decagonal axis. So, the ternary systems aluminum, cobalt aluminum, nickel aluminum and aluminum, cobalt aluminum, copper aluminum, these are characterized by the formation of decagonal phases. Here no icosahedral phases are observed. So, the field of decagonal phase is elongated with respect to a widely varying nickel to cobalt ratio, while variation of Al content is minimal. If we compare on the homologous temperature scale, the diffusivities of copper and nickel in the decagonal Al and ICO and the vacancy mediate self diffusivities of metallic cobalt and nickel are very close to each other. Whereas diffusion of gallium in these alloys is several orders of magnitude faster than the diffusion of transition elements cobalt and nickel. So, this we also saw previously for the AlPdMn type of quasicrystals, that the transition elements diffuse much slower than the non-transition elements. So, the combination of the crystalline and quasicrystalline order makes decagonal NiCO intriguing from the viewpoint of the diffusion mechanisms. As we said that quasicrystalline order exists only in the layers perpendicular to the decagonal axis, whereas crystalline order prevails parallel to the decagonal axis. So, if a diffusion mechanism specific to quasi-periodic order dominates, one should expect that the diffusion within layers perpendicular to the decagonal axis is faster than parallel to it. So, if the quasi-periodic order is present in the perpendicular to decagonal axis, and if the diffusion mechanism is also the one which is specific to the quasi-periodic order, then definitely the diffusion will be faster perpendicular to the decagonal axis. Then again, if a contribution of phasons comes into picture, if phazon mediated diffusion is present, then it will cause diffusion anisotropy with slower diffusion in the direction of the decagonal axis. And the anisotropy of cobalt and nickel diffusion is very small in the case of these quasicrystals. And the magnitude of diffusion anisotropy of cobalt and nickel in decagonal Al and ICO is like the anisotropies reported for the uniaxial metals as well. So, here is we have collected or we have put some of the data which has been taken by the references, just to give you a flavor of some of the studies that are done in these for different quasicrystals like icosahedral AlPdMn, ZnMgHO, ZnMgy, then decagonal AlNiCO, which are the tracers which are used. The temperature range, you can see these are the temperature ranges in which the diffusion studies have been done, and you can see the activation energies here. Okay, so here you can see, for example, these for the transition elements, if you see that the activation energies are much higher than if you compare the gallium in these decagonal phases, which is what we discussed previously, and so on. So, with this we will end our discussion on the diffusion in quasicrystalline structures and talk about the metallic alloys in the next video.